we're going to talk about a problem that Donna asked me a few weeks ago that I think is really interesting and that doesn't appear anyplace in your book, and you can't find in any of the problem sets. So here's a question. Let's say you have a set with n elements. I'm going to ask two questions that I hope everybody does know the answer to. Question 1. How many subsets are there? And question 2, how many permutations? Okay, so who wants to take a shot at this one? How many subsets are there? Michael?
2 to the n.
Right, there's 2 to the n subsets. We only have done this in 2 to the n different ways this semester, right? There's subsets, the number of binary strings, the number of rows in a truth table, etc., etc. There's a gazillion different ways of thinking of the number of subsets of a set with n elements, and the number is 2 to the n. You're distributing types of 0 or 1 into n distinct boxes. There's a lot of different ways of looking at it. It's 2 to the n. That's true. How many permutations are there? N factorial, right. And permutations of n elements. Right, the whole set. Permute them all. So these are 2 of the really basic things that we've used as building blocks in all the counting stuff we've done. So she asked me, hey, so how many ways are there to choose subsets when you do care about the order? Kind of a combination of these 2 things. This is just subsets. We don't care about the order that we choose the subsets, right? We care about the first one, the third one, and the fifth one out of all the n. The first, the 8th, and the 9th, and the 10th. But what if I care about the order that I choose them in? Well, obviously, it's going to be bigger than this, right? What's more, it's going to be bigger than this, too. Because just take the case where I take the subset of the whole set. The number of ways to order that is equal to n factorial. So if I'm interested, so I could look at this in a generalization in 2 ways. Ordering the subsets. There she is. I'm doing your question that you asked me 2 weeks ago.
Well, it's on tape right here.
Now you're right. You can wave to the camera. This is Donna's sequence here. Or you can look at it this way. Here's the number of permutation of all the elements. How many permutations are there if I take some subset of them? Okay? Where I can take any subset I want. They're the same question. I can either generalize from here or generalize from here. But it's a generalization of these 2 things. And it's so natural. I mean, it's the most obvious thing I think someone would think about, not to take anything away from your cleverness, because it's not in the book and it's not in any of the problem sets. So what's the answer? How many ways are there to order any subset of elements from a set of n?
Wouldn't it be the sum of like n choose 1 plus n choose 2 plus n choose 3 up through and not n but n permutation rather. Like n1, 2, and 3,
How many ordered subsets? So Chris has an idea, which is on the right track. Well, let's go through your idea. We want to divide this up into cases. Chris is going to sum up a bunch of cases. And that's the only way that I can see of doing this. Why don't we go through the cases where we have all the elements as a subset? How many ways are there to order all the elements? N factorial. Okay? That's one end. Let's go to the other end. I'm not taking any of the elements. Okay? There's one way if I take none of the elements. Right? That's... call it 0 factorial. That's 1. Now let's say I take one element. There's one way to permute one element, 1 factorial, but I can take lots of different elements. How many can I take? N, or n choose 1. So I'm going to write this out actually here too, n choose 0 if nobody minds, just to keep things steady. And this is going to be n choose n. What's the next one? I'm going to take 2 elements. I can take 2 elements in n choose 2 different ways, and I can order them each in 2 factorial ways. So I get n choose 2 times 2 factorial, etc. This is not such a crazy sequence. It's pretty straightforward, and that's the answer. There's
N choose 2 times 2 factorial is the same as permutation of n times.
right. This is the same as Pn0 plus Pn1 plus Pn2 all the way up to Pnn. That's right, Chris. Everybody remember what these, this is the permutation of this many things from n elements. This is taking the combinations and multiplying through by the thing we divided through to get the combinations in the first place. So it's this sequence. It's not such a bizarre sequence to have added up to begin with. Right? I mean, we have added up the sequence of Cn0 and Cn1. Anybody remember what that is? Cn0 plus Cn1 plus Cn2 plus... That equals 2 to the n. That's all the number of different ways there are of taking subsets. You take none, you take 1, you take 2, you take 3, you take 4, you take n. This is one of the first things we did. And then we spent lots of combinatorial identities. So why don't you do this? I don't know why. It's not in there. Somebody must know this and think that this is just completely trivial. But nobody I asked thinks so yet. So in the meantime, let's look at it. So here's the answer. Well, this answer is fine. I'll call it... what should we call it? How many ordered subsets? We'll call it, I don't know, T. I've got a better name than T. Mr. T. Ordered means that I care about the order. So it's like if I have 3 elements, 1, 2 counts, 2, 1 counts, things like that. All right. Well, I don't want to spend too much time on this. I'm going to do this for about another 5 minutes, but I just want to tell you what I've found out about this and what is true. You can fiddle with this a little bit with the algebra, and here's what happens. You can factor out an n from here to the right. And if you factor out an n from here to the right, here's what happens. T of n equals, this part is 1, plus n And here's what happens when you factor out the n and you rearrange the terms, and you can check this yourself. What happens is that all these terms go down by exactly one value of n. So it looks like this. If I get it right. If you multiply this n back through, you'll get this. And if you're wondering, is that really true, check it yourself. I think it's really true, and you can check it yourself if you want. And if you play enough with it, you'll see that it's true. So what does this tell you? It tells you that T of n equals 1 plus n times Tn minus 1. Because this is the same as this with n minus 1s replaced with the n's. Okay, this is the same as all of this with n minus 1 in place of the n's. So here's a recurrence equation. Is this a linear homogeneous recurrence equation? Because it doesn't have these constant coefficients. If this were a 2 or a 3, we could solve it. But it's not. It's an n. This makes it very hard to solve. Nobody knows a closed form formula for this as far as I can tell. As far as I know, nobody has a simple closed form formula. But there is a really nice thing you can do with this, because it's very close to a similar recurrence for derangements. And I want to make this connection and then show you something about the T of n here, and then we'll let this go as an interesting problem. So here's the derangement recurrence equation that I never proved, but it's true. We could prove it if I had time and this was the direction we'd want to go. Whoops. Oh, pause here. Here's a recurrence equation for derangements. It's exactly the same as this one, except instead of adding 1, sometimes you add 1, sometimes you subtract 1, alternating each time. if you remember, here's what we got for d of n. We got that d of n equaled n factorial 1 minus 1 plus 1 over 2 factorial minus 1 over 3 factorial. Did I get this right? Get this right. I think this is right. Plus 1 over 4 factorial minus 1 over 5 factorial, etc. 1 over n factorial. Remember we did something like this, and then we proved that this goes to e to the minus 1? Right, so the number of derangements was 1 over e times the total number of n factorials. If you do the same thing in this example, and you factor this thing out, you pull out an n factorial, and you're all done, here's what you get. T of n equals n factorial. Instead of them alternating minuses and pluses, you just get pluses. And what does this equal? As n goes to infinity, this equals e. Not e to the minus 1, just regular old e. That's from the Taylor series. So that means, what happens to the number of permutations when you allow taking subsets, or what happens to the number of subsets when you allow taking permutations? You used to have 2 to the n, you had n factorial, and when you answer the third question, as n goes to infinity, no closed form formula for particular n, but as n gets larger and larger, it ends up being e times n factorial. That's kind of a cool place where e shows up. That if you just go ahead and take all the subsets and you care about the order, you multiply the number of permutations by about 2.7. That's as far as I know anything about this problem. There seems to be a relationship to derangements where the pluses and minus alternate here, and here they just get pluses, but I don't see any combinatorial connection. I don't see why taking permutations and caring about when none of them get fixed has anything to do with taking all the possible subsets and looking at their order. I'm not sure why those connect. And if they do connect, it's a subtle connection because it's changing these minuses to pluses. But anyhow, I don't want you to feel like when you study all this stuff that it's all just there from day one like a Bible, and you sit and learn it and everybody knows it. Nobody really knows, as far as I know, from my email context, anything about this, any more than you guys know right now. And maybe I'll find somebody who's worked on this, and maybe not. But for what it's worth, now you know the answer. So when you ask me, how many different subsets are there, when you care about the order, the answer is between 2 and 3 times n factorial. All right? Questions about this? I'm going to switch gears for a second. So this was a little review, a question that Donna came up with, and I'm going to pursue it a little more and see if I can find somebody who can tell me more about it. Like I said before, discrete probability is 98% counting and 2% understanding probability. So let me fill in the 2%, and then we can go through some examples. If you want to know the chance of something happening, you can go through all sorts of mathematical definitions and be very formal about it. And in fact, you probably should at some level. But for the purposes of what we need to do today, it's a very, very intuitive kind of idea. If you want to get the chance of something happening, you count all the possible things that might happen, and you count of those which ones are the ones that meet your criterion. So, if I have a coin, and it's got heads and tails on it, and I flip it up in the air, there are 2 possible things that might happen, heads or tails. Say I want heads, the chance of that happening is 1 out of 2. It's too basic to go through. Let's do a die. I throw a die. It's got 6 sides. 6 possible things might happen. The chance of me, say, getting a 1 or a 3 is 2 of those things. So the probability of me getting a 1 or a 3 is 2 divided by 6, or 1/3. That's all you have to know about probability for now. Yeah.
What happens if the die is loaded or the coin is flat?
Then somebody shoots you. We'd have to make a more careful analysis. We're going to get at the end of the day to something called conditional probability. And actually, there's a way to test whether a die is loaded or not. You look at the outcomes, and you say, hey, what's the chance if I spin this die of getting 4 6s when it's a fair die? And you can calculate, what's the chance that I just got 4 6s in a row when it's a fair die? In fact, let's do it right now. I just spun 4 6s in a row. What's the chance of that happening? Well, when I spin 4 6s in a row, there are how many possible outcomes? Any possible 1 through 6, 4 different times. Okay? This is counting. So that's, who can do it? 6. 6 to the 4th. It's like numbers with 6 possible digits, and there's 4 digits. 6 to the 4th possible ways of spinning 4 dice and looking at the outcomes. How many of those ways give all 6s? 1. So the probability of getting 4 6s in a row is 1 divided by 6 to the 4th. Pretty slim. But it's possible. In your life, if you spin a lot of dice, you probably will have gotten 4 6s in a row at some point or another. It's only 1 out of 1,296 chance. It's not too unusual. You can even calculate this probably. What if I spun a die 1,296 times? What's the chance of this happening once? Kind of a meta question, but it's still within the ballpark. We could even do that, but let's hold off on it. Let's do some simpler things first. All right. Simpler question. I'm throwing free throws. I'm not so good. I got 50% chance to get my free throw in.
Shaq.
Yeah, I'm better than he is. What does he think when he misses 50% of his free throws? Does he think that it's okay? What does he think?
He has $120 million.
Just got paid $40,000 for that.
Okay. Easy question. What's the chance that you throw 5 throws and they all go in?
1 out of 2 to the 5th.
1 chance that they all go in. 2 to the 5th chances total. Misses and hits. Okay? So there's 32 different ways that he could hit or miss during those 5, 2 to the 5th, and 1 of them works. So not so likely. 1 out of 32 chances if I keep throwing 5 shots that I'll get all 5 in. No, I'll get it once in a while. All right. What's the chance that I'll get 4 out of 5 in? Same deal, 50%. What's the chance that I get 4 out of 5? Same denominator. 2 to the 5th ways of throwing misses and hits. 5 different times. How many of them?
5 different ways of,
Yeah, go ahead, Chris.
there are 5 different ways of choosing which of those ones is going to be your miss.
Good, good. Or another way to look at it, the same kind of idea, but a complement. If I have a sequence of 5 and I want 4 of them to be hits, I got 5 spots, and think of the hits as ones. I want to know how many ways are there to choose 1 miss or to choose 4 hits. 5 choose 4, or 5 choose 1. So I'll put 5 choose 1 here. So that's 5 over 32 to get 4 out of 5. How about 3 out of 5? 5 choose 2, or 5 choose 3, same thing, out of 2 to the 5th. That equals 10 out of 32. Okay, questions so far? Yeah.
Is there a reason you're choosing sort of the complement? So when you say 3 out of 5, and you say 5 choose 2?
No, because that's just the way
That's just what
Chris said. Yeah, so I went with him. But you could do it the other way. Which is more likely, if you can get 50% of your shots in, to get 4 of them in or to get 1 of them in, if you took 5 shots? They're the same, right? It's no more likely that you'll do better than your average than it is that you'll do less than your average. And that makes sense. What?
Depends whether if I was shooting, I'd be more likely to get less.
People unclear on the idea of average. That's right. Right. In a bowling league, you always want your average to be going up. So you want to do bad at the beginning because they give you a handicap. So you don't want to do really well at the beginning and then, well, when you all get older and join bowling leagues, you'll know what I mean. All right, questions about this? Who gets it? Everybody gets it? Am I right that it's 98% counting and 2% new idea? I think that's about the right percentage. There'll be a little new idea coming up, but not much. In the context of learning how to read math, I asked you to read this little article about this birthday paradox, and I want to review it now that you've got all this counting behind you. So we're going to review this not like a bunch of beginners who are reading math for the first time, but like people who can do a lot of hard counting problems, and we're going to analyze this problem in a sophisticated way. The problem is the following. You have a bunch of people in a room. You're wondering, what's the probability that 2 or more of us have the same birthday? Okay? And it turns out that this surprises most people. That once you get past, I forget what the number is, 32 or so? Anybody remember the number? 23? I think, yeah, for 50%. 23? So when you get 23 people in a room, the chance of 2 or more of them having the same birthday is 50%. When you have more than 23 people in a room, it's greater than 50%. When you have about 50 people in a room, it's very high already, the chance of 2 or more people having the same birthday. And most people have a gut instinct that this doesn't really make sense, that you would expect the percentage to be less. And unlike some other things we do, this is a good thing to make a couple bucks on if you need a drink at a bar and you got a rich friend who doesn't know much math. Or is just looking for an excuse to buy you a drink. All right, so how do we do it? How do we analyze this? It is hard to count the actual number of ways for us to have 2 or more people having the same birthday. We'd have to count the number of ways for 2 people that have the same birthday and for nobody else to have the same birthday. Then we'd have to count 3 people or more having the same birthday. There's a lot of possibilities, and it just seems daunting. So whenever it seems hard, you do the complement trick. You count the opposite. Instead of counting how many people 2 or more have the same birthday, why don't we count the opposite of that? That no 2 people have the same birthday. That's much easier to count. And then we'll subtract that from the total number of possible sets of birthdays that people could have. So let's back up. What are the total number of possible sequences of birthdays? Let's say I have 36 people in the room. Each of you could have a birthday from 1 to 365. Okay, no leap years today. Yeah, Neil, a question?
You have to say something about how the people get in the room. Right? You can't just pick a bunch of people and do this probability checking.
Sure. What do you?
Say they're all you just pick all these people that were born on the same day. They'll be in the room. I mean, they have to be picked randomly from some kind of.
Yeah, they're random people, right? Right. I didn't go to the November birthday club meeting. No. No. What do you mean exactly?
No, I mean, probability has to be like introduced in the problem before you can calculate it.
Well, only if you care about really being rigorous. We got a bunch of random people. I pulled them off the street.
Well, that's like essential though for the problem.
I agree. Right. The chance of any sequence of birthdays is as likely as the chance of any other sequence of birthdays. I have to say that, and we're assuming that. Okay. We'll assume that's true. So say I've got 36 people, and I want to calculate how many different possible birthday sequences I have. You know, starting with Peter, then going to Michael, and going around the whole room. How many different possible birthday sequences? Peter's got 365 choices. Michael's got 365 choices. All around the room 36 times. So how many total? Is that right? Who agrees? 365. That's like, instead of putting binary numbers in each slot, I'm putting 365 possible digits in each slot, and I've got 36 slots. This is the total number of possible birthday sequences. It's a lot. It's a huge number. I'm not going to actually enumerate them. Those of you who when you get nervous on a problem set, figure, okay, well, now I'll just list them. You're not going to be able to do it here. This is too big. We have to be able to analyze this in a more general way. Scheme could do it, yes. Okay, how many of these have 2 or more birthdays the same? That's hard to count. But how many have nobody the same? That we can definitely count. How many have nobody the same? Well, Peter's got the first choice. He can have 365 choices for his birthday. But if I insist on counting how many where nobody's got the same birthday, then Michael's only got 364 choices here. So what's the number that goes on top? 365. Is it factorial? Because I only go down 36 times, right? So it is up to a point. 365 times 364 times 363. Okay, smarty pants. Good. It's P 365, comma 36. Good. Now that you're fancy, you can write that. Good. All right. Well, now what? Well, that's the probability that nobody's got the same birthday. But we want the probability that two or more do have the same birthday. So all we have to do is subtract that from 1. Or equivalently, put 365 to the 36 up here and subtract P. That's the same thing. And this is the whole paradox. Go ahead and calculate. See what you get. Now, actually, if you go on a calculator and type in 365 to the 36, that's pretty silly because your calculator will buzz out and lose lots of accuracy. But you could calculate this because, as you can see, it's 365 divided by 365 times 364 divided by 365. So if you calculated each fraction as you went along and did it as a product, you could actually do it on a calculator and get an answer. And you'd get a percentage. And that's it. There's no paradox here. You just do the calculation and see. And if it's not what you thought, well, then fix your intuition. Because this really is true. Are there questions about this?
Is there a closed form for permutation the way there is for a sum, like a triangle number? Can I say what is the product of 36 consecutive numbers? Or an approximation for them?
Not that I know of. No. And if there were, then we could probably do that earlier problem today too. I don't know of any. Questions about this? Okay, good. What happens as the number of people gets very, very big? Well, what happens? Say this 36 gets very, very large. You know, it gets to be 365. Is it a certainty when it gets to be 365? No, this becomes n factorial, right? And this becomes 365 to the n, right? More or less. Well, it becomes 365 factorial over 365 to the 365. And that's a number. It's not certainty. Right? And if you just kept making this bigger and bigger and bigger and bigger, well, what happens?
But when you get 365, you get 366.
When at 366, you should have certainty, right? So what happens? We'd expect this to turn into certainty after a while, right? Does it? Well, if we want the whole...
How do you define taking the probability of more items than you have?
Well, we can't. Right.
So if that goes to 0, if the permutations of 365, 366 is 0, then it goes to 1.
Right. If you have to take more than you actually have, then the number of ways to do it is 0. So the probability of having 2 or more people with the same birthday becomes 1. You should always do that boundary case analysis whenever you get an answer that can be generalized, because it will confirm to you whether your answer originally makes sense. Let's do another example like this from the problem set that you've already finished. 2N socks in a drawer. You're pulling out 2 socks. You want to know what's the chance you get a pair. We calculated yesterday that it's 2n choose 2 divided by 2 times n choose 2 divided by 2n choose 2. This is the total number of ways of choosing a pair of socks. This is the total number of ways of choosing a pair of blue and then choosing a pair of red. You add them together. What happens to this as the number of socks in the drawer gets very large? If you calculate this, what does this end up being? Anybody remember? Did you do the problem set? What does it end up being? Something like this? Is that right? If it's not, somebody calculated and corrected. If this is true, then when n gets very large, what happens to this fraction? Where does it tend to go? This is limits from calculus. It goes to a half, right? So that means if you've got a huge drawer of socks and it's just bigger and bigger and bigger, the chance of you getting a pair is about 50%, which is just what somebody might have guessed if you gave them the problem for 10, even though it's not 50% for 10. It's only 50% as n goes to infinity, but it's not 50% for any other number. It's not 50% for any particular number. Is it bigger or less than 50% for any real number? It's always a little less than 50%, right? This heads to 1/2 from the bottom. Here's a question I haven't done with you yet, and it's going to relate back to the number of binary trees, the number of ways to multiply n+1 matrices, and the number of ways to set up k pairs of balanced parentheses, or n pairs of balanced parentheses. So it'll be related in a particularly unexpected way. And it also relates in an unexpected way to derangements. So this is a really cool problem. And it's one that originally I came up with on some test I gave, I don't know, some 20 years ago in some beginner computer science class. And like a lot of things I put on tests, weeks later I realized that there's some good stuff on it, and I didn't realize it when I first gave the problem. So here it is. It's the World Series. World Series is a 7-game series, for those of you not from this country or from this world. The first team to win 4 games wins the series. You got to win the majority of the games. There's a lot of tournaments like this. 2 out of 3, 3 out of 5, 4 out of 7, 5 out of 9. You can generalize it. Okay, so let's say we have a World Series. Doesn't have to be the real World Series, but well, let's make it the real World Series. 7 games. What's the chance, even teams now, even chances to win every game. Teams are evenly matched. What's the chance the World Series goes all the way? That means goes to the 7th game. People always wonder whether it's going to go to the 7th game. It affects whether the Simpsons premiere is going to come on Monday or the following Monday. It affects whether these commercials are going to be on that people spend $10 million on. It affects whether the bookies in Las Vegas are going to have lots of business. It affects a million things. It's actually practical. So, what's the chance when you start the series that it's going to go all 7 games? Let's calculate that. Everybody with me? All right. What are the total number of ways we could play 7 games in this series? That is, I'm team 1, Chris is team 2. We play each other. Either I win or he wins. Right? And we do this 7 times. How many sequences can we get? 2 to the 7th. It's just number of binary numbers with 7 slots. And that's some number that we can actually calculate.
Are you concerned with the first 6 because the first 6 determine whether you play the 7th? So if we have 3 wins for each team in the first 6, then we have to go to the 7th. And the 7th one, it doesn't matter what happens there.
That's true. And we'll do that up here. So you're saying, why don't we divide by 2 to the 6th? Because we want to know, if I play 7 games, how many of them have 3 wins and 3 losses in the first 6 places.
But if you just did it for the first 6 places, you could just check for how many have 3 wins.
The only real reason to go to the 2 to the 7th is if we're concerned with who wins after the 7 games.
But you also have to look at all the outcomes of the 3-2 games and the 3-1 series.
Well, the last game doesn't tell you whether you get to it or not.
Right.
And taking 2 to the 7th, you're considering the last game.
I think that's so.
Yeah, 2 to the 7th.
Rather than answering this question,
Why don't you just assume all games are played and whatever happens?
that's a nice way of trying to express. This really is the right way to do it, but I want to convince you that it is, because your question is very subtle and it's not so easy to answer. The way I'm going to answer it is, first I'm going to tell you what Jacob just said, and then I'm going to head and I'm going to do it for a very small case. So you'll see why this makes sense for the small case, and then I think you can extrapolate to here. But let's assume we've played the World Series. And I want to know, that's what Jacob just said. We've played the 7-game series. It's over. How many of them ended up being 3-3 before the 7th game? Okay? Now, sometimes it's going to end after 4 games. Right? That's true. But that represents a lot of the possible sequences of 7. We just don't play the last 3. But they could have been anything, and it wouldn't have mattered. This is a little tricky.
Is it not true that either way would work, though? Couldn't you do it for just the first 6 games?
If we did 6 permute 3 over 2 to 6.
Let's go ahead and do it. Let's go ahead and finish this, and then we'll calculate smaller cases. So here are the total number of ways there are to play a 7-game series. Okay? I flip a die that has I flip a coin 7 times, and I get, say, 0, 1, 1, 1, 0, 1, 1, 2, 3, 4, 5, 6. Right, but I flip it 7 times. I finish. Now, did this series go all the way or not? No, right? Because it ended right here. All right? Some of these sequences of 7 games are going to go all the way, and some won't. Or I should say it this way. Some would have gone all the way, and some would not have. I want to calculate how many of these sequences of 7 wins and losses actually make me play the full 7 games. Actually care. Think of this as Florida. All right? And this is Iowa, and this is Arizona. I do all the electoral votes. They're all done. How many of the states do I really care about when I'm all done? I still do it all, and now I look to see which ones make a difference and which ones don't. So I just won't play those other games if I don't need to, but to calculate the probability, I still need to look at them. All right, so how many ways have, in these 7 sequences, have 3 zeros and 3 ones? I got 7 places. I want to know how many of them have exactly 3 zeros and exactly 3 ones. How can we do that?
They can't have exactly 3 zeros and 3 ones. They have to have 3 or 4.
In the 7 sequences, there's the first 6 places have to, right. The first 6 have to have 3 zeros and 3 ones. I said it wrong, right. The first 6 places have to have 3 zeros and 3 ones. How do you do that? 6 choose 3. Is that it? How many different ways are there of taking 6 digits and putting 3 zeros and 3 ones in them? I got 3 choices for the ones, anywhere I want to put them. That's 6 choose 3. And when I'm done with that, I got no choices for the zeros. They just have to go in the other spot. So 6 choose 3 is it. Let's calculate this. The bottom is 128, and the top is 20, right? What is this? I think that's right? So in a World Series, at the beginning, from the start, the chance of reaching a 7-game series where the first 6 games are split 3-3 is 5 over 32, about 1/6. And we can go back and look at all the World Series for the last 100 years and see how many of them went all the way and how many didn't. And we would expect in the long run for it to be about a 6th going the whole way and the rest not.
Not necessarily, because you assume the chances here of winning
Are equal, right.
equal and independent of the...
Right. That's true.
That probably doesn't hold.
Maybe not. We'd have to find out, right. Right. That's true, especially for the Yankees in the 40s, right? 50s. Or lately, right. That's it. Right.
Although you have to double that because
How is that Tris speaker doing nowadays? I'm doing my Monty Burns imitation.
possibilities, so you have to double that.
We have to double this?
Yeah. The 7th game has 2 possibilities. If you're actually figuring all the...
If you say the odds of it going to
But doesn't
the
matter.
7th game, then we don't get it.
Yeah, it's played 7 games, doesn't care who won the 7th game.
Right, but there's one possibility with the 7th game being won by Team A, and there's one possibility with the 7th game being lost by Team A.
We could figure out how many series go 4 games, 5 games.
I agree with Doug. What do you think about that? He's right.
We could test it. Easy to say.
Or else we could do what Chris said before. We could change the 7 to a Either we change a 7 to a 6, or we say that once I've put these 3 zeros and 3 1s in these places, that the next spot could be either a 0, or it could be a 1. Either I didn't count this right, or I didn't count this right. I gotta be consistent. So let me back up. So what we have here is wrong. This is the number of ways to put 3 zeros and 3 1s into the first 6 places. This is the total number of strings of 7 wins and losses. But this is not the total subset of these that have 3 1s and 3 zeros in them, because it doesn't include the very last position being either a 0 or a 1. So we really would have to put a 2 in here. And that's the same as taking a 2 away from here. And maybe that's what you were asking at the very beginning. You were saying, why don't we just think about the first 6 and then wonder about how many ways there are of putting half of those in as white and black. So does that, you feel good about it now? This really is right, and this is really wrong.
So the chance of going 7 games is a third?
About a third. Yeah, sorry everybody. We were careless, and I was the most careless.
With evenly matched teams.
Evenly matched teams, about a third. That's in a World Series of 7 games. So we're going to do this again in a World Series of more than this many games. We're going to see what happens as n gets bigger and bigger and bigger. As you increase the number of games in a series, what do you think? What's the chance that it goes all the way? You think it's going to go down? You think it's going to get less and less? You think it's going to average out? Here, let's calculate it for 3-game series. Who can do it for 3 games? 2 to the 2, and up here is, this is a 3-game series. Okay, it's either a win-loss or a loss-win. So this is 2 over 4, 50% that it goes all the way in a 3-game series. What's the chance it goes all the way in a 1-game series? 100%. So 100%, 50%, and when you're down here in a World Series of 7 games, it's down to about a third. Does it keep getting less? Does it level out? What happens? Let's calculate it. We're going to calculate it. We're going to get something a little bit surprising. Well, maybe not so surprising. Are there questions so far? So EJ and Chris, you were ahead of me here, and now you're happy?
I'm going to give that one to Doug.
You're giving that one to Doug. All right. Okay, take a bow. That's right. All right. Let's solve this in general. I got a World Series, instead of 7 games, it's 2n plus 1 games. Okay? So in this case, the n was, what's the n in this case for a real World Series? 3, right? 2 times 3 plus 1, 7. So in general, what would the formula end up being? The bottom is 2 to the 2n, and the top is 2n choose. Good. We're going to work with this for a little bit. And instead of me saying, okay, just do the algebra yourself, today we're actually going to do the algebra because I think it's important. Let's write down what we calculated before. If n is 1, that means it's a 3-game series. What was the probability of it going all the way? Half. And when it's a 5-game series, we didn't do that. Can someone do that and check? When it was a 7-game series, we calculated it was 5/16. I think that's right. Somebody check that.
But when we get to 7,
Somebody check it. Is it right? Don't trust me.
HX says yes.
HX says yes? Okay. Nobody sees a pattern yet. How do I know what the next one's going to be without looking?
Some kind of funky power of 2 on the bottom.
Some kind of power of 2 on the bottom. And what happens on the top? It's tricky, huh? I kind of hid the pattern a little bit because I converted everything to lowest terms as I went along. And if I hadn't, I wouldn't have hid it so much. But here's what actually happened. This is a half. This is a half times 3/4. This is a half times 3/4 times 5/6. This is a half times 3/4 times 5/6 times 7/8. Does that all work out? So if you want to know what it turns out to be at any point, just put the odd numbers on the top, the even numbers in the bottom, and multiply your product as you go along. It couldn't be more iterative and also more obscure. Why does this turn out to be this? So I want to show you why, and it's really not obscure. We're going to fiddle with this, and we're going to turn this into exactly one of these sequences. And in doing so, it's going to help us with a lot of approximations somewhere else where this number comes up. This is a key number in understanding number of binary trees and understanding balanced parentheses and understanding how to multiply matrices. This number comes up, and being able to approximate it is important. And the fact that it has something to do with this sequence of odds and evens is kind of neat. Okay, questions so far? Yeah, Tony.
That 2n over n was the series that we did in our problem set 5, right?
We did a proof that this equals the sum. Do you remember the proof we did? That this equals the sum of, good memory, well, almost a good memory. Remember this proof? I asked Sam this, and it was the one thing he said this whole semester that he didn't know off the bat, is if you add these up without the squares, it equals 2 to the n. If you add them up with the squares, it equals 2n choose n. Remember that you had to prove that? Well, that's neat. We're not going to use that right now, but it's neat. Well, you got this 2 to the n on the bottom. Let's fiddle with this a little bit. Factorial things are kind of easy to fiddle with. Lots of things cancel. Let's play with it and see what we can do. All right, 2n choose n. Turn that into factorials for me. 2n factorial divided by n factorial times n factorial, right? Divided by n factorial times n factorial. So I'm going to put those 2n factorials, if you don't mind, on the bottom. Okay, next to this. So n factorial, and okay. Let's just do that for now. Let's just work with this. 2n choose n. Let's just work with this. We'll throw this in at the end and fix it. All right, now what? How can we fix this up, make it nice, and get odds and evens out of it? What does 2n factorial look like? Let's take an example. Say n is 4. All right, it's 8 times 7 times 6 times 5 times 4. All right, so let's go ahead and pull out a factor of 2 from something like that. Let's look at an example. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I could pull out a 2 from all the even terms. Right? If I do, what happens? What do I get if I do that? How many 2's do I pull out? N in general. In this case, 2 to the 4th. And what's left? I got 1, 3, 5, 7 times 7, 5, 3, 1 times 4, 3, 4, 3, 2, 1. Ugh. Is it going to be useful or not? Let's see. I'm going to do it now in general.
2 to the 4th? How did you get 2 to the 4th?
I pulled out a 2 from here, and a 2 from here, and a 2 from here, and a 2 from here.
Oh, okay.
I pulled out 4 of the 2's out front, and I left myself with a nice factorial and a bunch of odd numbers. But you see those odd numbers? That's what I'm hoping to look for. That's why I did this. I'm looking for those odd numbers, so there they are. let's do this in general. Let's do the top now with n's. 2n factorial, I can take out 2 to the n from that. What's left? N factorial is left, times what? Times those odd numbers. 1, 3, 5, up to what odd number? 2n minus 1. Good. And on the bottom, I still got n factorial, n factorial. All right, so one of them gets canceled out. That's pleasant. Bye-bye. Bye-bye. Okay, now we're going to take this guy and put him in. Okay, this 2 to the 2 to the n that's been sitting out and waiting. Let's get rid of this. Get rid of this. 2 to the n times 1, 3, 5 up to 2n minus 1 divided by n factorial divided by 2 to the 2n. Now I'm ready to manipulate that. We're almost done. Two to the n and 2 to the 2n. What happens there? I got n2s on the top. I got 2 n2s on the bottom. N of them disappear from the top. They're all gone. And I'm left with just 2 to the n on the bottom. So that's also nice. Bye-bye. But look at here. I got n2s. I got n factorial. Now I'm going to put all the 2's back in here. So if this n factorial is like 4 factorial, 4, 3, 2, 1, now I'm going to put the 2's back in, and I'm going to get 8, 6, 4, 2. These are just going to be the even numbers starting from 2n. Let's try it. 1, 3, 5 up to 2n minus 1. And on the bottom, 2n is going to be the biggest number I have. And I start from 2, 4, 6, all the way up to 2n. And that's what these numbers are. So that funny-looking equation turns out to this infinite product. Very different ways of looking at the same thing, but they're really completely identical. And again, this last step is distributing these 2's back into the n factorial, so you get the even numbers from 2 to 2n. Okay, so if you want to know the probability of a World Series going all the way, you could put large n into here and calculate it. What if I ask you what happens to this as n gets very large? It might not be obvious what happens to this as n gets very large. But if you see it like this, it might be more obvious. What's going on here? Maybe, maybe not. What's happening here?
The denominator's getting larger.
Right, you're always multiplying by some other fraction. A fraction closer and closer to 1, it's true, but it's always by 7/8, and then by 9/10, and then by 10/12. So what's happening to the overall product as you go along? It's always getting smaller. It's still not clear that it doesn't level out, but I think either on your problem set or on some, no, it's probably a thing I thought of putting on an exam. You can prove by induction that this ends up being smaller than like 1 to the 2 to the something. In other words, you can prove by induction that this actually is smaller than something which strictly gets smaller and smaller and smaller and smaller. In other words, this really does go to 0. The chance of you making it all the way in a series where the number of games is longer and longer and longer is less and less and less. The chance of it happening tends to 0 as the games tend to 1,000, 10,000, 100,000. Namely, parentheses of n pairs, how many balanced ways, number of ways to multiply matrices, to multiply n plus 1 square matrices, the number of binary trees with n nodes. These are all the same. you proved in one of your problem sets that these two were the same. Remember that? And I just told you that this was the same as these two. I'm going to talk a little bit more what it is today. But I want to tell you the answer to this because we're going to prove what this answer is later on when we do our last topic on all this stuff, when we finish probability. But I want to give you the answer in advance. The number of ways to do all these three things is 2n choose n divided by n plus 1. Let's do an example. If you have 3 pairs of parentheses, or 3 nodes for a binary tree, or 4 square matrices that you want to multiply together, how many different ways are there to do it? Anybody remember? 3 balanced parentheses, 3 binary trees, how many different ways? 5, right. Good memory, Jeff. Right, 5. Let's put 3 in here and check that. 6 choose 3 is 20. 20 divided by 4 is 5. Right, so this works. It's correct. Proof by single example. And these are called the Catalan numbers. They come up in lots of places, so they got a name. Just like Fibonacci numbers have a name because they come up in lots of places. In your problem set this week, one of the problems is to get some kind of big order growth for this function, 2n choose n divided by n plus 1. And the way to do it is to use what we did over here to show that we know that 2 to the n choose n over 2 to the 2n, that this is equal exactly to this fraction, right? Using this equaling this is a way to get an approximation here. Okay, there's one way to do it. So you should be able to connect these two ideas. We're going to talk about this idea much, much more in a little bit, but I have another topic in between. Are there questions so far? I'm going to talk a little bit more about this, and I'm going to finish up with probability. Any questions about?
What did you say the numbers were called?
They're called Catalan numbers. C-A-T-A-L-A-N. I want to remind you of something you've done on the problem set before. I asked you on the problem set to prove some recurrence equation about these two. Actually, it was about this one, the square matrices. Then I asked you to show that this was one-to-one correspondence with this one, so that they're really the same, and the same recurrence equation would hold for this one. Anybody remember what the recurrence equation was here? What Cn depended on? I'll give you a hint. It had to do with where the last multiplication was. You could do any sub-multiplication of all of them, then the last multiplication, followed by any sub-multiplication of the arrays that were left over. So what did that end up being? C1 times Cn minus 1 plus C2 times Cn minus 2, all the way up to Cn minus 1, C1. And that's the same as what I think Michael was calling out. I equals 1 to n minus 1 of C I Cn minus I. I think that's right. Let me double check it. 1n minus 1, 2n minus 2, n minus 1. Yeah, that looks right. Remember that recurrence equation? Yeah, do we have the foggiest, vaguest idea of how to solve such a twisted sister?
Are these, is this a series of choosing?
No, these C's are these Catalan numbers, are the same as... It's the number of ways to balance parentheses of n pairs of parentheses, n minus 1 pairs of parentheses, etc.
What do they look like when you write them out? Capital letters?
What are they? They get big really fast.
4, 8,
They're what are they? 1, 2, 5, and then like 13, 14, and then some big number. They get big fast. They grow quickly. I don't know the first few by heart. All right. Well, solving a recurrence like this is daunting. I mean, nothing that we've done so far works. Not linear homogeneous, not substitution, not proving by induction. I mean, everything just falls apart. And we are going to be able to solve this, but we need a new tool, and we'll get to it later. But before I get there, I just want to add one more thing before I let this go and then come back to this later on. The one thing that's left over that we still have to finish up is, how come binary trees have anything to do with this? And why are binary trees in the same category besides the fact that I just told you they were? Well, here's why. Let's say I want to build binary trees with n nodes. How can I build them? How can I build them and get the same recurrence equation? We'll call it Bn, number of binary trees with n nodes. What does it depend on? Think recursively here. How do you build up a binary tree with one extra node? I'll give you a hint. Don't put it at the bottom. That's harder to do. Put the new node at the top. How many new ways can I make a new binary tree? I always put the new node at the top. Okay, there it is. How can I continue? I got two sides, right? The left side can be any binary tree as long as it has well, the sum of the two have to have n minus 1. So I can put any tree here and any tree here. I'll call this T1 and T2, as long as the sum of T1 and T2's nodes equals n minus 1. Well, there's a lot of possibilities there. B1, Bn minus 1. B2, Bn minus 2. B3, Bn minus 3. All the way up to how many ways can I get n minus 1 vertices on the left and 1 vertex on the right? It's the exact same recurrence equation. It's the exact same idea. The binary tree idea, because you're balancing left and right, and you want the sum of those two to be n minus 1, gives you the same exact recurrence as this.
It has the same ends, even though that's going to, because we want n minus 1, right? Or it sort of works out.
No, it is the same ends. Look. The first possibility is that we put all the trees with one node on the left, and all the trees with n minus... Oh, did I do this? Uh-oh.
Well, this is from going from n to n plus 1.
Yes, it's going to be
Oh, it's fine. It's okay.
You can think of...
Yeah, so call this n plus 1, right?
There you go.
Now I'm okay.
No.
No?
No.
Now it's now n minus 1. Right. Okay. But that's not quite the same.
You really have to count trees of 0 nodes as well.
Yeah.
Oh, I do. Right.
We put everything
Right. Right. Thank you, EJ. I got saved by EJ. Good. So this is B0, B, n minus 1 plus. All right, so it's going to look like that. Still not the same, but it should be the same.
Did we write this T in because one numbers correct?
Ooh, you got to wonder. I think we did. Oh, maybe we didn't.
I start at 0 rather than...
Yeah, maybe they're the same. Yeah, maybe I wrote these wrong. Oh, now I have to reconstruct those. Sorry.
Some of the subscripts in the catalog numbers equal n, and some of them in the binary tree now we've got them equal n.
Right, but it's more likely that this is wrong than this is wrong. I made a mistake in one of these, but I forget which one. Let's go back and redo this. I tried to do this from memory from your P set, and maybe we can redo it. A1, A2, A3, A4. All right, if I want to figure out the number of ways to associate A1, A2, A3, A4, I can group them, say, here's the last multiplication. Right, so this would be C1, C3, and I'm trying to do C4, so they should add up. So that looks right. Oh, I know what the difference is. It's in this situation, it's n plus 1 matrices and n vertices. We didn't do anything wrong, but I forgot to In this situation, the Cn refers to having it work for n plus 1 matrices, and for n pairs of parentheses, and for n binary trees. So that takes care of this extra. No, not exactly. Oh, I'll have to come back to this when I really do it. I thought I would fill this in now and it would make it better, and I just filled it in and made it worse. When I do this problem and actually solve this recurrence for you, which I will do very soon, not today, but soon, I'll come back and redo this and show you the connection to binary trees. But you'll have to take my word for it today. They really are the same. I didn't prove it today. I made this error, but I'll back up and do it soon. Yeah. Baruch, you had a question? Tony.
To find all the possibilities of a binary tree of height n,
Of height n.
given all the possible subtrees in addition to whatever you have of that height, could you use the formula we did for the rectangles where we had the series, the sum of the series,
Yeah.
and square what you end up with?
I'm not sure.
You should mention using a similar formula to this one.
Yeah.
Or are you speaking only of the Catalan numbers? Are you saying you can only use the Catalan numbers to do this?
The Catalan numbers are the number of ways there are to do this.
Right.
So what we generally are doing is trying to get the one with n vertices to be dependent on one whose sum of the subtrees is n minus 1 vertices. Not whose heights are n minus 1, but whose sum of the actual vertices themselves are n minus 1. So I don't think we can do a product like that. But like I said, let me get back to this. This is not this really was meant to be a short diversion to lead you into it when I do it next time. But what I really want to do is finish up probability things today. There's one idea here, but I want to motivate it to make sure you all get it. It's not a complicated idea, but it can be a little bit subtle in its applications. It's called conditional probability. Instead of me asking, hey, what's the chance of this happening, you just count all the outcomes and you count how many work out to the ones you want, I'm asking you a different kind of question. I'm saying, I'm giving you that this happened. What's the probability that this other event is true, given that this happened? So it can change your probability. Here's an example. Here's a very famous example that people always present as puzzles that you can probably find in some Ask Marilyn Vos Savant column in Parade magazine. This is the kind of thing she likes to talk about. So here it is. And then she goes on, explaining in the most completely obscure way about why the thing's true, appealing to trust me as the main reason. I don't like her because she makes everybody feel like...
And then she says, I'm stupid.
Well, I just think she makes math seem more magical than it should be, rather than just explaining how it really works.
She wouldn't have a job.
Oh, she's got a good job. And she certainly understands the things herself. And to her credit, when the famous Let's Make a Deal puzzle that relates to probability here came about, and do you know that one? I'll tell you. You play Let's Make a Deal? You ever see Let's Make a Deal? What? Okay, so you talk about it in recitation. Fine. It's a good puzzle, but basically when you first hear it, your intuition is to guess the wrong answer. But what was worse is that some PhDs actually wrote her some letters chastising her, saying she got it wrong. And if there's one thing she doesn't do, she doesn't get things wrong. She's pretty bright, and she usually knows what she's talking about. She has no clue usually how to explain it or how to make it comprehensible. She just makes it seem transparent, and for anybody who doesn't understand math, it just reinforces the idea that, well, I'll never really understand it, so I should just keep talking vaguely, and sooner or later someone will say, yeah, you get it. And I hate that. But she does get the answers right, and she had all these letters from people who should know better saying that she was wrong and explaining that she didn't understand it. And in fact, they didn't understand it, or they just mistakenly talked too quickly. But we're not talking about that. We're talking about something different. Tara will talk about that maybe today. Here's a famous example. All right, here's an easy one. You walk up to a box. Somebody says there's a child in that box. They say, what's the chance that child's a boy? Equally likely it's a boy or a girl here. You say 50%. What's the chance of it's being a girl? You say 50%. You're right. No big deal. All right. Now,
What is the kid doing in a box?
all right, we have to, little motivation. All right. Here we go. You walk up to somebody's house. You're an undercover agent. You've got a big SWAT team behind you. You bang on the door. Presumably, this family is keeping a child in a box, and you want to save the child. It's twisted humor, I know, but we need it. That's perfect. All right, there we go. My imagination could not be actually stranger than life, right? All right, so here we go. You walk into this house, and you knock on the door, and it got a suspicious-looking box in the corner there. So, and then you see this little kid run across the hall, and you see it's a girl. And your SWAT team leader says, "Should we open the box? What's the chance you think it's a girl or a boy?" And you say to the woman at the door, "How many children do you have?" And she says, "I have 2 children." And you say, "Well, I see your other child's a girl." And she goes, "Yeah, that's true." And then you say, "Well, you're under arrest, and we're about to open that box." And what's the chance that the child in the box is a girl? 50%. It seems like 50%, right? Now, same situation, but we come into the house, same exact thing. There's a box in the corner. There's a kid in the box. That little kid runs across the way. It's a girl. And you walk up to the woman, you tell her she's under arrest, you introduce yourself. You say, "Oh, what a nice little girl you have, the one that you saw running." And she goes, "Oh, yes, that's my oldest. She's very sweet. I have 2 kids." And what's the chance the girl in the box is the kid in the box is a boy or a girl? It's not 100% it's a girl. But the probability here changes. There's a big difference if you just know she has another kid before you make your decision about the probability than if you know her older kid is the girl. There's 2 conditions here. One condition is you know she has another child, and that's all she has. And the second condition is you know she has an older child who's a girl. Your first gut instinct when you hear this question is, well, it's still 50%, but it's not. And it really isn't. You could do this experiment and convince yourself it really isn't. You need a SWAT team. Let's calculate. Let's calculate it logically without booing any formulas up on the board, how you calculate conditional probabilities. It's very logical. Conditional probabilities mean that I've told you something is true. So the number of your outcomes, of possible outcomes, has now changed. Here's what I mean. This woman has 2 kids. What are the possible outcomes for her children? Normally, it'd be 2 boys. Normally, it'd be boy, 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 girl, girl, boy, or girl, girl. Right? That's normally. Now, when you saw that she had one other kid, and that kid was a girl, which of the probabilities remain? This one's gone. That is not one of our possible outcomes anymore. You have been told that that is not a possible outcome. It could be any one of these. Out of those, we're going to calculate how many have the other one being a girl. What's the answer? Just this one, right? Not 50%. What about this case? The case when I told you the older one's a girl. What are the possibilities? The older one's a girl.
1 out of 2.
So in this case, the original case I told you that you figure, oh, it's 50%. It's not really 50%. It's really a third. And in the second case, where I told you the oldest one is a girl, it's really a half. Right? This is really strange, right? So forget the stuff with the kid in the box for a second. Just think about all the friends you have that have 2 kids. If their first kid is a girl, if their oldest one's a girl, the chance that the second one's a girl also is 1 out of 2. Okay, if you get a girl, the chance of having a girl the next kid is still 1 out of 2. But if I tell you, I've got a whole bunch of friends, they all have 2 kids, they all have at least 1 girl. What's the chance the other one's a girl? And you can do this experiment. Get all your friends that have 2 kids that have at least 1 girl, put them in a big pool, and count the number of people that have 2 girls. It's going to be only 1/3, not 1/2. So this is subtle, even though it's a simple case. And it's not what you originally feel or your gut instinct is. But you can calculate it. Here it is. Here's all the possibilities where somebody's got at least 1 girl. Here's the only one where they have 2 girls. So if I tell you somebody's got at least 1 girl in the family, exactly 2 children, 1/3 of a chance they have 2 girls. If I tell you that the oldest one's a girl, then it's down to 1/2. It's weird, right? What if I didn't say the oldest one's a girl? What if I said, let's forget the oldest. What if we said, here's more of a philosophical issue. What if I said, that's the one with freckles? What if what did you gain from here, right? I mean, the person told me that's the oldest one, right? And suddenly my probability changed. What if they told me something else about that one? Just something unique that separates it from another one. It wouldn't tell you anything, right? Well, it would tell you something if you knew that every family only had 1 freckled kid, and once you had a freckled kid, you couldn't have another freckled kid. It would actually tell you something. Because then if you had the freckled kid at the beginning, it would give you the same different number of outcomes. So you have to be careful. The reason this matters is because you can only have 1 oldest kid. All right, maybe that's not particularly illuminating. But this is really right.
So you're better off having less information. You're better off
Depends.
knowing that, because you can guess boy, the other.
What do you mean better off? You mean
that you can have better. If you guess girl, not knowing whether the girl is the oldest, you have a 2/3 chance of being right. Right?
You're better off if you're guessing girl.
Right. So
if you're guessing boy, sorry.
You're better off if you're guessing boy.
The probabilities change. The idea of better, you're putting a judgment on it as to whether you're going to get the answer right or not, I guess. Let's say you're always going to guess boy, then if somebody tells you that the oldest one's a girl, you're down a 50-50 shot. If somebody doesn't tell you the oldest one's a girl, then you should be guessing boy. If they don't tell you information, then you have a better bet. But that's not so surprising. Sometimes giving you more information lets you have less of a choice about what you want to bet on. In fact, that's how the stock market works. The more information there is, the less likely you are to be able to make the right decision. It's just random. The more information there is in the stock market, the more random the stock market will seem. The more completely perfect every price will be. So that if you bet on either side, it's just going to be a random bet. It's the less information you get that actually lets you leverage. Well, now we're really getting twisted out of shape.
Just the problem, really quick.
Yeah. Somebody shoot that guy and put him in a box.
Is it a guy? So the mother says that the kid that walked by is her oldest.
Right.
Okay, and that changes it from a.
That changes from a 50. Well, that makes it a 1/3 chance that the other one's a girl. If she tells you the oldest one. No, sorry. If she tells you the oldest one's a girl, that changes it to 50-50 that the other one's a girl. If she just tells you that's my other kid who walked by, then it's only a 1/3 chance that the other one's a girl. No, yeah, Ixnay on the twins.
If she said it was the youngest, you would still.
Yeah, sorry, yeah.
There's trouble with the notion of probability here, because it's a boy or a girl on the bottom. There's no probability that it's a boy or a girl. 80% of the time there's going to be a boy and a girl.
No, there is, sure. Why? No, there is, sure. I mean, what if I had a whole block full of twisted families, and every one of them...
The problem is one box. One family walking...
Right, but we're assuming that the chance of them having a boy, girl, boy, girl is completely arbitrary, completely random.
Well, then you can talk about probability.
Right, so... Right.
The primary assumption that
If
there's
everybody
50%,
had a child in
there's
a box and you
an equal
randomly
number of
selected
boys
a
and
bonus
girls.
score.
Right. The primary assumption is that there's an equal number of boys and girls in the world, and every person who has 2 kids can have boy, 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 girl, girl, boy, girl, girl equally.
Just like there's a fundamental problem in psychology of this,
Yeah.
where they take a static, like, room full of people and do probability calculations, and it's like incorrect. I mean, because you have to have probability to compute probability. You know, so they do all kinds of
Well,
experiments. in psychology.
you're talking about something important. You're talking about statistics. You're talking about if you take a sample, how do you know that that sample is a reasonable reflection of a real random sample, and how do you test that? And you can calculate probabilities that a sample you took is really reflecting the bigger population. But
No, I suppose the definition of probability is like the way you did it, or it's based on relative frequencies, like limits in a series. Observations, go on and on and on. But the probability is defined as the limit, not as a ratio of favorable to unfavorable. That's like the issue.
But it's okay to define it as the ratio of favorable to total. It works out as long as.
No, it doesn't work out.
Why not?
You can't talk about the probability of getting like a biased coin. If the coin's biased, you can't define it.
But this isn't biased. These are boys and girls, and there's a 50-50 shot.
In general, you can't talk about situations that don't have that ratio of favorable to unfavorable cases.
All right, I'm not really
The biased point is defined as if you throw it for infinite number of times, it's the proportion of times it turns up in. It's not a ratio. It's not a ratio of favorable to unfavorable cases.
I think maybe it's because we're importing the idea that there is, in fact, an even chance of having a boy or a girl, and that we're basing everything else on that probability.
That's true, and we're also basing it on the same assumption, the fact that a coin is going to be half heads, half tails. We're assuming that's true. What's the chance a number from 1 to 20, inclusive, for those of you who don't like the word between, problem 1 to 20 is divisible by 3. What's the probability a number 1 to 20 is divisible by 3? There's 20 possibilities for the number. How many of them are divisible by 3? 3, 6, 9, 12, 15, 18. 6, so 3/10. Now let's switch it a little bit. Given, not that the other one's a girl or that one's a boy, but given that a number is divisible by 5, what's the probability? Same question. That a number 1 to 20 is divisible by 3. You're given that a number is divisible by 5. I'm granting you that fact. The number is definitely divisible by 5. What's the chance that a number picked between 1 and 20 is going to be divisible by 3, assuming that it's divisible by 5? Let's calculate that.
4 possibilities.
How many possibilities are there for the number? It's divisible by 5, so 5, 10, 15, and 20, right? 4. And how many of them are divisible by 3? 5, 10, 15, 20, only 15. So in every one of these examples, I'm just trying to motivate for you that the definition of conditional probability really does just cut down the total outcomes and then cut down the appropriate number of possible things in the numerator as well. But there's something general that's going on here that I want to show you in this example that generalizes in a way that you can't always just use this simple approach. On the top here are the number that are divisible by 5 and divisible by 3 and are between 1 and 20. And there's one of those numbers, right? The number divisible by 5, divisible by 3, and between 1 and 20. And on the bottom is what? The number divisible by 5 and between 1 and 20. So based on this, there's a different way to look at this. Very much going to be the same answer, but what's the chance, given a number between 1 and 20, that it's divisible by 5 and 3? That's going to be 1 out of 20. And what's the chance that out of the numbers 1 and 20 that you get things divisible by 5? That's going to be 4 out of 20. And that's the same as 1/4. Two different ways to look at it. One is counting all of these explicitly, counting all of these explicitly. And one is counting the probability here and dividing by the probability here. Here's our total possibilities. Here are the ones that are divisible by 5 and 3. Here are the ones that are divisible by 5. So I want to write...
Do you think of this changing your total case? Right? Just change.
Yeah, I think of it kind of normalizing over some base case. But now I'm going to write up a formula that's the basis of all conditional probability, and then we're going to end with this. The probability of something happening conditional that something else has already happened. The probability of A on condition of B. A in this case is divisible by 3, conditional that it's divisible by 5. This is the condition, this is the probability you're looking for. It's equal to the probability of something divided by the probability of something else. What's on the bottom, what's on the top? Base this example to construct this rule for yourselves. On the bottom is going to be the probability of the condition. And on the top is going to be the probability of the intersection of your two events. Both A and B. This is the famous theorem about conditional probability. I present it to you in this way because I want you to see that it's intuitive, that it's not just something arbitrary that you have to memorize. It just makes sense. We'll do one quick example, then we'll quit today. Same thing, given divisible by 5, what's the chance the number is divisible by 3? But this time, I'm not going to tell you that the number is between 1 and 20. Any number at all. Everybody with me? So I'm giving you that a number is divisible by 5. What's the chance that the number is divisible by 3? What do you think that chance should be? If I gave you any number, what's the chance that it's divisible by 3? 1/3. Either it's divisible by 3 or divisible by 3 remainder 1 or divisible by 3 remainder 2. They're all equally likely. So we'd figure it's 1/3. If I tell you that the number is divisible by 5, that doesn't seem to tell you anything about whether it's divisible by 3 or not. It just seems to be picking a random sequence. Or is it? Well, let's calculate. This is for any number. What's the chance that a number is divisible by 5? That's the condition. That goes in the bottom. What's the chance that a number is divisible by both 3 and 5? If it's divisible by both 3 and 5, that means it's divisible by 15. That's the only thing it could be. So this is 1/15. And that equals 1/3. So it really is 1/3. This worked because 3 and 5 are relatively prime. If you can divide a number by 6, you can definitely divide the number by 3. So it should be 100%. Let's use our little formula and just check out the limit cases. It's always a good thing to do. The chance that it's going to be divisible by 6 is the condition. That goes in the bottom. That's 1/6. What's the chance that a number is divisible by 6 and the number is divisible by 3? Now in this case, they're not relatively prime. So the chance of a number being divisible by 6 and being divisible by 3 is exactly the same as the chance of it being divisible by 6. So you got a 6 divided by 6. The intersection here just collapses and becomes uninteresting, and you get 1. Okay. This is what you really need to know to do any of the conditional probabilities that I gave you in the P set. Most of them are a lot more involved than these basic examples, and maybe I'll have Tara try to do a couple examples of this, go over the exam, talk about the let's make a deal problem. We're up to here. We're what day is it today? We got Monday? We have 2 days left this week. Here's where I'd like to be at the end of this week. I have one important lecture on generating functions, which is a topic in and of itself that will relate back to those Catalan numbers. That'll take a day. Then I'm really ready to start off on the last week's material. So we're more or less ahead and we can slow down a little bit. I'm going to have Tara, and maybe I will also, at the end of this week, kind of do a review of all counting, of all probability, make sure everybody's ready for number theory and cryptography. Problem set 6 is due before you go away for Thanksgiving. Get it done. Finish it. Problem set 7. There's only one more problem set. There's that roaming card trick problem set. Those two problem sets are due any time before the end of the month. All right, so pace yourself. Try to get the card trick one done early in the week. Leave the other one for later. The final is the very last day of the month, and it will be comprehensive, but it will be much more toward the things that I haven't tested on yet. So we'll cover things about probability and counting. It will cover just a little bit, maybe one question about logic and one question about recurrence equations, but it'll be mostly about counting and some stuff about number theory at the end. Okay, that's the big picture. All right.
Is there a chapter on relative probability in the book?
Unconditional probability?
Sorry.
I think there must be a section, right. There's a good section in the algorithms book, in the Revest book. The Revest book, like I said, has this chapter at the beginning on discrete math, which is really dense, but is actually, in many ways, a complete introduction to discrete math.